ஸ்கிரீன் பிரசன்ட் பண்ணி பார்க்கவா?
பிரசன்ட் பண்ணுங்க சார்.
பண்ணி பாருங்க சார். செக் பண்ணிக்கோங்க.
ஓகே. ஸ்கிரீன் தெரியுதா மேடம்?
தெரியுது.
ஓகே.
நான் இன்னும் பிரசன்டேஷன் வரல.
சார் என்ட்ரன்ஸ்
விசிபிள் மேடம்?
எஸ் சார்.
ஓகே. ஸ்க்ரோல் ஆகுது இல்ல மேடம்?
எப்படி இதுல வரல?
எஸ் சார்.
மேபி கொஞ்சம் டைம் கேப் ஆகுதுன்னு நினைக்கிறேன். என்ன மேடம்?
வருது. கோமதி அவர்களை பின் பண்ணும். பிபிடி பின் பண்ணுங்க. டீம் ஆரம்பிச்சிருக்கீங்க.
இது கரெக்டா இருக்குல்ல மேடம்? இப்போ வந்து உங்களுக்கு டைம் கேப் ஆகுதுன்னு நினைக்கிறேன். ஒரு 1 செகண்ட் 2 செகண்ட் வந்து கொஞ்சம் ஸ்லோ ஆகுதுன்னு நினைக்கிறேன் ஸ்க்ரோல் பண்ணும்போது.
எஸ் சார், ஒன்றும் ப்ராப்ளம் இல்லைங்க சார். நல்லா வருது.
ஓகேங்க சார்.
ஓகே மேடம். ஸ்கிரீன் இருக்குமா மேடம்? இந்த ஸ்டாப் ஷேர் பண்ணவா மேடம்?
இப்போ வந்து நீங்க ஸ்டாப் பண்ணணும்.
ஓகே, ஸ்டாப் பண்ணிடுறேன்.
உட்காருங்கப்பா.
Madam, YouTube live also anything going on, madam? Actually, yes. My students, they are trying, but they are telling link is full.
Sir, shall we share the link, sir?
Can you share the link, madam? Just for my students.
Thank you, sir.
Okay, madam. Okay. Thank you, madam.
Thank you. வேணுமா உனக்கு கூட வந்துட்டு இங்க பேச அங்க வருது.
அனுப்பிச்சாச்சுங்க சார்.
வந்துருச்சு மேடம்.
ஓகே சார்.
குரூப்ல போட்டு.
Two minutes.
So shall we start, sir?
Yes, madam.
Okay.
Happy morning to all. Jubilees are occasions to be celebrated to recall the marvelous ways in which the Department of Chemistry has fulfilled its missions in imparting education, moral, and discipline. Yes, in commemoration with the Golden Jubilee Year of Celebration, PG and Research Department of Chemistry (DKMC) organizes national level webinar on recent trends and advances in organic synthesis. I would like to invite Dr. M. Nagaratna Ma'am, Aide and Associate Professor of Chemistry, to inaugurate the webinar.
Good morning to all. In commemoration with our college Golden Jubilee celebrations, our department has planned to organize a webinar series. I congratulate the organizing committee members, especially Dr. Santalakshmi and Dr. T. Gomati, who are the organizing secretaries. My congratulations to our chief guest, Dr. T. Kumaraguru, scientist, Biocatalysis Lab, Department of Organic Synthesis and Process Chemistry, Indian Institute of Chemical Technology, Hyderabad. Sir, feel privileged to have you for this week. Our students are eagerly waiting to hear your lecture, which is going to motivate them for their future career. Thank you, sir. Thank you all participants.
Thank you, ma'am, for your valuable inaugural address. Next, I would like to invite Dr. Shantalakshmi Ma'am, Additional Controller and Assistant Professor of Chemistry, to deliver the welcome address and also to introduce the resource person for today's session.
Thank you, Sharanya. Good morning to all. On behalf of the PG and Research Department of Chemistry, DKM College for Women, Vellore, it's my pleasure to welcome you all to this webinar on recent trends and advances in organic synthesis. I would like to welcome our Madam Principal, Dr. P.N. Sudha, Head of the Department of Chemistry, Dr. M. Nagaratna Madam, and the resource person, Dr. T. Kumaraguru, Scientist, CSIR IICT, Hyderabad. I extend my warm welcome to all the faculty and student participants of other colleges as well as the faculty of our college and my dear students. Albert Einstein said, education is not the learning of facts, but training the minds to think. Hence, to enrich the knowledge of our students, we, the Department of Chemistry, is organizing the lectures, seminars, conferences, and competitions periodically. I would like to share a few words about our department and our college. DKM College for Women was founded by Amarar Vellore N. Krishnasamy Mudaliyar in the year 1972 for the upliftment of women. At present, DKM College for Women offers 19 UG courses, 12 PG courses, 10 MPhil, and 11 PhD courses. The Department of Chemistry was established in the year 1972 as PUC, and now it is upgraded as PG and Research Department. Our department staff members publish around 300 research articles at various reputed journals and 52 book chapters. Total grants received for minor and major projects by our department staff members from various funding agencies is rupees 56,37,500. And number of MPhil students produced by our department is 79. Dr. P.N. Sudha, Principal, guided 38 PhD scholars, and at present, we are guiding 5 PhD scholars. At this juncture, we would like to wish Dr. P.N. Sudha, Principal and Associate Professor of Chemistry, who is listed in the top 2% scientists in polymers by Stanford University. Congratulations, ma'am. As a part of the Golden Jubilee celebrations of our college, we, the Department of Chemistry, organizes this webinar series And we would like to dedicate the same to our beloved founder, Thiru N. Krishnaswamy Mudaliyar. For today's webinar, we are glad to have Dr. T. Kubaraguru, Scientist, Biocatalysis Lab, Department of Organic Synthesis and Process Chemistry, CSIR, Indian Institute of Chemical Technology, Hyderabad, as a resource person. He procured his PhD degree in Organic Chemistry at IICT Hyderabad in the year 2009. He is a university rank holder both in UG as well as in PG. He has received a Senior Research Fellowship from ICMR, New Delhi, and a Star Performance Award for Biocatalysis work from Dr. Reddy's lab. From 2006 to 2009, he worked as a research executive at Orchid Chemicals and Pharmaceuticals Limited, Chennai, then as a scientist in Biocatalysis Lab, Dr. Reddy's Laboratories Limited, Hyderabad, from 2014 to 2017. From 2019 onwards, he is working as a scientist in the Biocatalysis Lab of the Department of Organic Synthesis and Process Chemistry, CSIR IICT, Hyderabad. His expertise in the process development of API intermediates using enzymes, enzyme immobilization techniques, bioanalytical process development, and studies on scale-up issues and support for plant-scale production and intellectual property rights. He is guiding 4 PhD scholars and he has published 14 papers in international journals with a high impact factors. He has completed CSIR sponsored projects of the amount of rupees 2 crores. At present, he is working with 2 IICT sponsored projects of an amount of rupees 1.1 crore. Above all, he has filed 5 patents to his credit. Congratulations, sir. So we are very glad to have such an eminent person as a resource person for today's program, and sir will be delivering a lecture on the topic recent trends and advances in organic synthesis. With this introduction, once again I welcome you all to this program. Now I request Dr. Kumaraguru sir to take over the session. Thank you.
Thank you, Madam, for your kind introduction and warm welcome. Today it is my privilege to be here for the Golden Jubilee celebration. Just to start my presentation. Yeah, thanks, Madam. Thank you for your organization and for arranging this wonderful seminar. And I wish you all the best for your Golden Jubilee celebration also. So today my topic is the recent trends and advances in organic synthesis. I'm audible, Madam? Yeah, okay, I can go. So this is my short introduction and my profile. And already Madam explained already. So this is actually what we are doing from CSIR, that today that COVID pandemic situation, what is our contribution from CSIR Institute. This left hand side that graph, it's showing that different institute and different their contribution. And we are from CSIR IICT Hyderabad. We are more into new repurposed drugs and RT-PCR enzyme supply and PPE. This is our contribution from CSIR IICT, and like other different CSIR institutes also, their contributions are this left hand side. And this is various departments R&D activities at CSIR IICT. So we have different departments, and I am from organic synthesis and process chemistry. Like we have animal applied biology, animal health, and environmental oriented research, fluoro agrochemicals, various departments we have. So I am part of organic synthesis and process chemistry, and we do have national malt bank facility. So which this facility has like all the library of around 60,000 small molecule and big molecule. We have a library of huge library, and we used to store at -20. And so even universities, colleges, academic people, they can use the facility. So anti-TB activity free of cost, we can able to give the data, and anti-cancer activity, that is a chargeable cost actually. Yes. So the contributors are this Pradhama Mainkar and Srigari, both of them are taking from our department. So before going to that topic, importance, what is the importance of fundamental research, technology, so-called process development, advancement, improvement, why we are doing actually these all the things and all. So if you don't want any technology or improvement or any science, actually this is the right hand side, life without science actually. So again, if you see that life with modern life and technology, so everybody would like to go with modern life and advanced technology, but again it is our choice that whether we should accommodate the technology or industry or no industry. That is all depends upon our purpose and our own interest actually. So this clearly shows that what is the importance of technology. Otherwise we have to leave it like again we have to go back to our olden times. And what is the importance of, apart from that, whether that environmental issue or technology, all the things, again one more problem is, biggest problem is now the trade war actually. So the trade war is now you can understand that more deeply in COVID pandemic situation, that China imported material even from mask onwards, mask, sanitizer and API, drugs, everything we struggle a lot actually. Now vaccine problem is the shortage of vaccine. So everywhere that is a shortage, because now that COVID pandemic situation, all the countries they need for self-sustained development technology. So we are in the running out of the competition actually. What we can do, otherwise if you are depending on imported material, the cost will be high and their demand also very high actually. So you can see that some news articles I just rise in imported API cost may lead to hike in drug prices. China threat to halt US antibiotic supply. And again, Chinese pollution also headache, because of that more industry, again lot of products, and they face the pollution issue. Because of that, the 40% of company industry also they are in need to close the industry 40%. Again, the price was increased. Again, the demand for importing problem also we are facing indirectly actually. For example, not only API, actually you can see that toys also, you can see that biggest market actually, electronics, toys. So here, if you see that there are few companies, JK Pharma belongs to our Kadalur, and even Archit Pharma also, now Pfizer took over. So they are all penicillin G production, antibiotic production. There are many key players, but now everybody closed because of the Chinese market and the price hike, everybody closed. So this is the right time for India to reduce the dependence on API imports from China or particularly from any other countries. That's why we need the technology or development, whatever the process development, we are in need of development. So presently, if you are seeing India, Make in India campaign is going on, effluent treatment plants and waste management, zero discharge, circular economy. Particularly, if you see that biomedical waste, now that COVID pandemic, one side we are able to handle with mask or any drugs or whatever vaccine, everything, but the other side we are increasing the biomedical waste. So we should be able to dispose the biomedical waste also in efficient way. That is also important actually. So why the demand is there? Why we are not able to have any self-sustained technology? Why we are not able to have in-house technology? That question always will be there, because we have a lot of institute, colleges, universities, IITs, IACs, CSR institute, but still what is the lack of behind that technology development? Just to show you that, you can see that there are publications, are there academic publications, there are that they used to develop some one part technology, one part process development, but that catalyst, if you see that 15 steps it need for, it's like a not commercially available catalyst. They used to develop with a large long step up catalyst they will develop, and complex catalyst that which is able to do one part transformation. But there is no industrial applicability. We see there is no industrial applicability. So that gap between the fundamental academic research and applied research is always that there is the gap is there. So starting onwards, during the development onwards, actually there is a collaboration required, strong collaboration required between the academic and as well as industry. What society need and what is we need to develop. So that the scientists and professors and who are into the research field, there should be a strong collaboration is required. And the second thing is, what we need is speed. We can't wait for longer time for the drug development, all the things. So it should be a right time. So collaboration, same time need. What is the need is speed actually. These two actions are important for that strong collaboration and process development. And from CSR initiative, already we initiated many of the, from IACT we are into the strong field of drug discovery. So, and API process development. So we already initiated some of the remdesivir we worked, and favipiravir we worked, and presently we tie up with Bharat Biotech also for the vaccine development. And recently you can see that even MI phone also, they are advertisement with coming with the Make in India theme. So these are some pictures what IACT develops in synthetic process for favipiravir, and we transfer the technology to CIPLA, and that even that CIPLA package also coming with IACT logo. So these are our contribution. And coming to the point, modern chemistry laboratory. So earlier days, if you see that when we are at some conical flask, some people, it is there that chemistry lab, we can climb as a chemistry lab. But now that modern chemistry lab, you need a lot of instrument. So earlier, intellectual driven process or driven technology. Now instrument driven research is going on actually most of the places. It's nothing wrong, but now students' expectation also more. They want sophisticated equipment, instrument. Otherwise, they are not willing to join also actually. So the laboratory need more equipment. So mostly it is now instrument driven research only going on. So that's why we are telling as a modern technology. So chemocatalysis, organometallics, organocatalysis, flow chemistry, biocatalysis, photochemistry, automation, AI. These are some of the most modern technology what is going on around the world. So particularly if we see that AI is the important field for the today modern chemistry technology. Actually, that what we are expecting is in future there is no need of any chemist also required to run the reaction. So instrument will take care. If you fix the target, it will give the scheme and it will add automation. Already started that kind of robotic model started already. So there is a bright future for artificial intelligence. And so what is the research, the similar model, what is going on around the world is particularly now that the nation's important is waste to wealth. So most of the people are focusing on biomass valorization and circular economy. So waste to wealth is now that so much biological waste is there, again biomass, kitchen waste, so many waste generation is because of our population, waste generation also more. So one side it is we are keep on dumping the waste, and that again that waste treatment cost also more. Okay, actually, so how to utilize the waste actually, that is the one kind of research is going on now. Many IITs also started focusing. And agrochemicals, again that olden days agrochemicals, now the demand is coming back again, and again bioremediation after using that pesticides, how to bioremediation properly actually, that by using some enzymes or microbial bioremediation or some chemical catalyst bioremediation, that kind of research also going on. Particularly water treatment also one kind of research. And photocatalysis, organocatalysis, as I mentioned, artificial intelligence. And I mentioned that some DOE, design of experiments and reaction progress kinetic analysis, RPKA. So this is all are now that the present initiation. So if you see many of the industry, they are not they stopped working on blindly some of the schemes. Suppose you want to optimize some solvent, you want to optimize with some temperature. Earlier days, just a student will they will run the experiment, maybe 600 to 700 reaction they will run, and they will write the data. What is the observation? Maybe what is the byproduct? What is the yield? What is the purity? But right now, what is the current scenario? Many of the industry adopted a design of experiments actually. So what is design of experiment? A systematic method to determine the relationship between factors affecting the process and output that process. It's like a mathematical model, probability calculation. So if you have like a three-way model, like solvent, temperature, and pressure, or some variable parameter, you can create a mathematical model and you can interpret the data. The software will give the right probability, right combination to run the reaction. So it is like a more or less software assisted organic synthesis. So in that way, your number of experiment will be reduced. You don't need to go for 100, 200 experiment. With the less number of experiment, you can achieve your target actually. So this is one kind of research now everybody adopted. In that way, you can save your time, and chemical utilization also. You can reduce the chemical consumption. So most of the MNCs already started adapting. Without DOE, they are not allowing to go for any reaction. And another thing, reaction progress kinetic analysis, I will explain you in later slides. So if anybody interested to understand more on DOE, maybe you can go through that paper publication, OPRD 2015. So that paper, maybe people note it, and you can go through that article later on. And flow chemistry. These are the recent trends in chemistry. Outside research is going on. And as a college, maybe I can also give some suggestion that already I know that Madam mentioned that so much research is going on in your universities. But I want to that slightly you can adapt it with the national interest also. It will be well and good. And you can see that the background, there is a word green chemistry is there. So even when the presentation also, they are more interested in green chemistry. So, but without green chemistry, there is no research, no recent technology, nothing. Everything for the godfather is the green chemistry only. So first I will explain about green chemistry. What is green chemistry and what is the relationship between that green chemistry and the modern technology? So green chemistry is nothing but green chemistry efficiently utilizes all the raw materials and eliminates waste and avoids use of toxic and hazardous reagent and solvents in the manufacture and application of chemical products. So nothing but if you are adding A and B, all the atoms utilizes properly to convert as a product C. So if something is going as a waste, that is not a green chemistry. And another also, operator safety also important. So that safety and that you should try to avoid hazardous reagent, toxic reagent. These are the main criteria of green chemistry. The term introduced by Professor Roger Selden, and that paper is Green Chemistry 2005. You can go through that article for more understanding about green chemistry. So that the history, how that green chemistry terms came, that also I will explain you. So it is a mnemonic for the spirit of green chemistry. How you will remember that green chemistry principle? There's a 12 principle for green chemistry. Whatever I mentioned, prevention instead of remediation, atom efficiency, less hazardous chemical use of less chemicals, design safer chemical products, safer solvents, auxiliaries, energy efficient by design, renewable raw materials, shorter synthesis. Synthetic routes should be very shorter, not like a very bulk 15-20 steps. Catalytic methodologies, use catalyst rather than stoichiometric amount. Design for degradation. So after that utilization, how that biodegradability of that your waste. Analysis for pollution prevention. Inherently safer chemistry, actually, that your process looks safe. So how to remember this, all the 12 principle? It's like a short term is productively. P for prevent waste, R for renewable materials. That raw material also should be available, sustainable, and omit derivatization steps. Avoid that number of steps will be increased. Blocking and deblocking, degradable chemical products, use of safe synthetic methods and catalytic reagents, temperature, pressure, ambient, and in-process monitoring. Very few auxiliary steps. E should be E factor and maximize speed in product. Low toxicity chemical products. Yes, safe means it's safe. So it's like a short term for how to remember that 12 green chemistry principle productively. And what is the history behind the green chemistry? In late 1970s, actually, somebody, if you are developing some process, I want to start industry. So what is the way your process is, how far it will be safe, and maybe it is economically viable or not. Maybe that idea not there in 1970s. So earlier what they used to call like a simple way of that atom utilization, syngas utilization. So that idea is just like very simple. More atoms of the syngas that ended up the product better, actually. So I will just tell you that example. Carbon monoxide methanol production, again you can see that methanol synthesis, for example, 100% syngas utilization, where ethylene uses only 44%. You can see that ethylene production 44% syngas utilization, remaining 56% going as a water. So you can see that molecular weight of this carbon monoxide and hydrogen. You can see that 44% only that product, remaining 56% is the byproduct. If you see that in the case of methanol, that 100% syngas utilization, carbon monoxide and hydrogen, there is no byproduct. So this is the simple way of calculation of your process is green or not green. So in 1970s, actually. So with that process, they went for one plant in 1980s. It is like again Netherlands-based industry. So that how that in that way only that Professor Roger Selden got the idea of that introducing the green chemistry concept. So here fluoroglycinol plant, actually they started one plant. The DSM company started that plant. Initially, the process, actually the plant, they started based on some vintage olden type chemistry, they started the plant, but immediately that they closed the plant also, because they, after starting the plant, after running the process, they understood that rather than the production cost, the waste treatment cost is more than that production cost, so it is not viable. They closed the plant also. So the process generated approximately 40 kg of solid waste containing chromium sulfate, ammonium chloride, ferrous chloride, and potassium bisulfate for every kg of fluoroglycinol. So it is like 1 kg of product, 40 kg of waste is generated. So I'm not going about more detail in the chemistry. I'm just giving the overall picture only. So just for understanding. So this is the fluoroglycinol manufacturing process that they went for the plant production. So so trinitrotoluene, the TNT started with TNT and potassium digromate and nitration, and again reduction with the ferrous and iron, and aqueous chloride, again it's a hydroxylation. So this is a vintage type, olden type chemistry. Without optimization, they went to plant, and that is the byproduct they received actually. So I will tell you again that E factor. So after closing the plant, they have a deep discussion. So how effectively, before going to the plant, how effectively we can avoid this kind of problem. So before starting the reaction, how we can judge that whether the process is economically viable, there will be no waste generation will be there. So after closing the plant only, they had a deep discussion and they discussed it with Professor Roger Selden. Then they came up with the concept that at the same time that ideas can come from different people, that this is actually not Roger Selden, William Trust in 1991. He introduced one term called atom economy. Atom economy is like a molecular weight of desired product divided by sum of molecular weight of starting material into 100. So it is nothing but 100. Suppose your molecular weight is 100, all the starting material, whatever that, like a syngas utilization only, all the sum of starting material, like again that is 100, then it is like your atom economy would be 100%. So it is nothing but 100% utilization of all the raw material. Okay, so he introduced the term called atom economy. Again, atom efficiency also, again multiply with yield, that is atom efficiency. So in all the green chemistry matrices, only the two factors are very famous. One is atom economy. Again, this is actually the drawback is it is not accountable for solvent, reagent, all the things and that. So you can call like a desired product divided by starting material, all the starting material, but what solvent you are replacing, how much purification solvent and the other reagents, that will not accountable. That is the one drawback. So another term that Roger Selden from Netherlands, this is 1991. Again, he introduced the term 1992. One of the conference he introduced the term called E factor. So now this is the E factor is the well-known famous factor for calculating the green chemistry matrices. What is E factor? That is a total waste divided by product kg. So our ideal value should be close to 0. 0 means zero wastage. For example, the chlorobilcinol product, 1 kg of product, they generated 40 kg of waste. So in that case, E factor is 40 divided by 1. So E factor is 40. So suppose E factor is 40 means per kg of product, they are generating 40 kg of waste. That is E factor. Another thing is process mass efficiency. PMA also he introduced it. Again, PMA is like a total mass of inputs divided by mass of product. It's equal to E factor plus 1. E factor ideal factor is 0. Then 0 plus 1, 1. So process mass efficiency 1 means it is a very good process. They introduced these two terms actually. So these four factors are very important matrices for analyzing your process is whether green or not. So today, entire process, mini process, the E factor running based on the calculation based on the E factor only. So this is a very important factor. Maybe you can read more on that in net. So in industry, pharma industry, most of the industries that if you see that oil refining 10 power 6 to 10 power 8 product tonnage, E factor is less than 0.1 kg. So bulk chemical 1 to 5 kg, fine chemical 5 to 50. Pharmaceutical, again, if you see that 25 to 100. So here that wastage will be more because of that purification. Pharmaceutical, you need that again, product quality also should be more, impurity profiling. Because of that lot of purification steps and chemical steps, E factor is more. So we are targeting green process for pharmaceutical development. So recent trends, again, I mentioned that what all the recent technologies are going on around the world. So biomass valorization, you can again see that there is nothing waste actually. So if we see that there is nothing called waste, it is important resource lying in the wrong place at the wrong time. That is called, we should not call nothing as a waste actually. So here biomass to feedstock, most of the research what is going on, it's a bioethanol and biogas production, anaerobic digestion, and again value added product, again biochar. So many research is going on around the world now. So you can also focus that what all the maybe that in around the area, what all the waste things are going on, how you can bring that to value added product and how you can treat that efficiently. So that kind of research, one of the important research, and it will be more oriented, society oriented also. In that aspect, actually, ILCT, we are working on biogas treatment, so methane production. So these are some of the pictures, and this governor visited recently our vegetable market. And this is the Bowenpalli is one of the biggest market in Telangana. So that whatever that kitchen market waste we are dumping into that anaerobic digester, and that finally we are producing methane gas, and it is supplying to that electricity production, and plus that around the area some kitchen use purpose LPG gas also they are supplying. Actually, these are some of the pictures. And the second thing is mechanochemistry. So though these all are not in my research area, I just want to tell you that what is kind of advanced techniques are now it is going on. These all are like olden techniques only, but again people are in like bringing into the new shape. So mechanochemistry, a force of synthesis, chemical synthesis enabled or sustained by mechanical force. It's a reawakening of solid state approaches to a solid state, olden days solid state chemical synthesis only. Now that new form is mechanochemistry. So in the mechanochemistry also, you no need of any hi-fi equipment. If you want to adopt some hi-fi equipment also, you can buy ball mill type, all the things. Otherwise also, it's like a small modern vessel is more than sufficient for this kind of research. So you can do good science by using that modern vessel, and so that driving force is by mechanical disruption, mechanical force. One of the case study, interesting article I have come across with the Nature Nanotechnology 2021 published. Maybe you can read this process more into the detail. So this paper deals with the Haber-Bosch process, that ammonia synthesis. This is a olden 1913 developed process actually. So for ammonia production, still now that process is industrial scalable process with high temperature, high process. This is the only one process without any modification running actually. There are other process, always improvement, modification, so many things are required. In this actually, by using the mechanochemistry, somebody published the paper by using iron catalyst and by nitrogen fixation, converting the nitrogen and reacting with hydrogen to ammonia. That is Haber process. They are just by using the ball mill and mechanochemistry, they published this paper. Again, their the original process is 400 to 500 degree at 100 bar pressure. They could be able to achieve 82% volume versus 25% volume at 450 degree and 200 bar. This is the industrial process, but they can able to achieve with 45 degree with 1 bar pressure. They can able to achieve 82.5% volume. This is they claimed, this Nature Nanotechnology paper claimed that they can able to do at lower temperature and lower pressure. So this is one of the breakthrough achievement by using mechanochemistry. So similar way you can think about more other area also, what way we can do. This is like again how it is related with green chemistry means, again you can see that there is a no solvent, less number of steps, and you are a safer process, avoiding the high temperature process. So it is again it is meeting the green chemistry metrics requirement. And another thing is photochemical reaction. Earlier days many photochemical reaction, it is like a replication of natural process, but recent days many criticism is there that what is the use of photochemistry, why people are, is there any use is there, and nobody use it for any industrial, what is the use like that is there. So here a chemical reaction initiated by absorption of energy in the form of light, that is called photochemical reaction. So how it is related to again green chemistry? Unlike chemical catalyst, reagents leaves behind no waste. Here you are not using any chemical reagent. Again, it is a waste generation. Again, you are not going to generate that waste treatment, bioremediation, nothing is there. So you are using as a light as a source for your reaction. Again, some of the cases highly reactive. You can see that the photochemical reaction, mostly a radical mechanism, it is like a highly reactive species will generate. It's generally in chemical reaction, if you want to generate some highly reactive species, you need high energy. So here by using light energy, you are generating high reactive species actually. That is like a operator safety process also. So in that way you can claim as a green chemistry process. And recently one of the article I come across with Natural Communications, photons as a 21st century reagent. And there are a lot of developments. Again, now the industry also started developing that large scale photochemical reactor, particularly combining with flow chemistry. There is a lot of research is going on. So for that you need some of the UV lamp or like a LED bulb also sufficient for to run the lab. So this area also one of the recent technology we can focus. Second, another thing is that flow chemistry. So what is flow chemistry? Flow chemistry, if you see again, earlier days, if you want to do some of the process, you need bigger reactor. Some tonnage, if you want to do, you need bigger container and a large filtration setup, large how to work up, all the things are required. So now the flow chemistry concept removed all the classical traditional kind of requirement. So flow chemistry is sometimes referred as a blood flow or continuous flow. So it's nothing but your reagents. What is that A and B? Your reagents, you are just mixing through the tubing actually. And this is the reactors. This is called reactor zone. and here this is a mixing your reagent A and B or C, whatever your reagents, it is mixing here, and this is a catalyst bed, your catalyst will be there. That concept is here. If you see that small in traditional way, your substrate will be more, catalyst will be less, but here it is a reverse actually. Your catalyst will be slightly more here filled in cartridge, but small amount of substrate is meeting at a time, so that efficiency, catalyst efficiency will be more here. Again, because of the back pressure, that resident time also will be more actually. That is, a force will be there, it will react, the colloidal will be more and it will react faster, and the conversion will be faster here, and there will be no side product, particularly in your reactions, traditional reactions in RB flask. Over the period 24 hours, 48 hours reaction, there is a byproduct formation will be there. But here it's a fractional 3 minutes, 2 minutes reaction only. We can depends upon your tube volume. Then your byproduct product quality also will be better, and impurity profiling will be less. Again, particularly flow chemistry, we can use for some kind of dangerous hazardous reaction, butyl lithium, palladium carbon reduction. So it's like it's inside the tubing and cartridge, there will be a no exploding kind of glass reactor explosion. That kind of probability also you can avoid. So reaction time, how that flow chemistry expression is in the term of residence time. Residence time nothing but your catalyst and your reactants, how much time it is meeting together. So residence time is given by the ratio of the volume of reactor and the volume of the reactor flow rate. So Dow is equal to V by Q. So this is called reactor zone. If your substrate stays in reactor zone more time, your efficiency will be more. Otherwise, you have to simply recirculate to again back to recirculation, so that you will get the 100% conversion. So here you can apply heat, cooling, electrochemistry, microwave, light, everything. If you apply light, is a photochemical flow reactor. For example, one of the case study is a ibuprofen anti-inflammatory drug actually. So they synthesized, first step is isobutyl benzene propanol chloride Friedel-Crafts acylation in flow. So solvent-free Friedel-Crafts acylation. Again, for flow chemistry also, always batch reaction is important. You have to develop the process, you have to optimize the process in RB flask, and you have to optimize the process, then only you have to convert into flow. Directly flow will not do any magic actually here. So that once that process optimized with solvent-free Friedel-Crafts acylation, again that is going for second step, it's like a 1 to aryl migration. Then after aryl migration, third step will be saponification, ester hydrolysis actually. So there is a 3 steps in flow simultaneously. Here membrane separator is there. Again workup also, that acid base workup is there. Again iodine monochloride promoter for 1 to aryl migration. Trimethyl orthoformate catalyst is there pumping through here, and iodine monochloride. So you have to optimize the process entirely in batch, and when we can introduce, where we can introduce. And maybe here if you see that unreacted propanol chloride or maybe unreacted aluminum chloride, so many possibilities there. That impact should be how that second step, that impact is there. Maybe triplic acid or HCl aqueous, what is the impact on second step? The excess reagent is there, how far it will impact, or otherwise you have to remove in between also, that how far involved. In batch, if you see this all the process, minimum 1 week it will take in plant. So mixing the 2 reaction, again 1 day overnight reaction, again workup, again cleaning the reactor, again you have to go for second step, again do the same process, again you have to clean the reactor, again you have to go for workup. So minimum it will take 1 week process, but in flow you can see the total reaction time is 3 minutes with 83% overall yield, and the productivity is 81 gram per hour. So these 2 papers you can get the more detail about flow chemistry. This organic process chemistry 2016. This is a review process. This is the angiochem process, but it depends only for that ibuprofen, how that they optimized the process actually. So this is also one of the modern chemistry. IICT we are dealing with this. We have more equipments with this kind of technology. So if you want to see 8.5 gram per hour, if you want to increase the productivity, maybe you can increase the tube volume. This is nothing but your tubing volume actually. If you increase the tube volume, or you can parallel reactor, you can just assemble the parallel reactor, then you can increase your productivity. So this is one. Another thing, earlier I mentioned that reaction progress kinetic analysis, RPKA. So this is like either you can go for artificial intelligence fully automated, or you can go for as a partial automated, semi-automation. So either DOE or this reaction progress kinetic analysis comes under partial automation. So what is that RPKA? It's a subset of broad range of kinetic analysis techniques utilized to determine the rate loss of chemical reaction and to aid elucidation of reaction mechanisms. So it is nothing but it's a huge, bigger, confusing terminology. So nothing but you have to visibly, you have to understand that what is going inside the reactor, inside that RB flask. You can't able to see that. You can only able to see that color changes or temperature, all the things. But what is going on telescopic view, what is going on inside the reactor, that is called RPKA. So it can give that information about mechanism and byproducts. So this is again Angiochem paper 2005. Can get more detail on this publication. Anybody interested in RPKA? So I will give you an example. So you can see that nitro 2, reduction is there. So how earlier way, maybe if you're like a classical way, if you want to, as a chemist, I want to monitor the reaction, either I will go for TLC, how that reaction is progressing. Second way is like a HPLC, I will go, or GC, I will go. So how the reaction is progressing and all. This is like a olden days technology. Before that, earlier people will monitor the reaction with UV spectroscopy or IR. The techniques now people are forgotten. Everybody going with modern technology. So again, bringing back to that olden technology in the new format. So what they are doing, FTIR spectroscopy follows the disappearance of nitro group. You can monitor based on the disappearance of nitro group, FTIR. So you can plot over the, so how that time versus conversion is there, based on the nitro group disappearance. So end of the reaction, you will get the 0. Again, hydrogen uptake, monitor stepwise stoichiometry of the hydrogenation. This reaction is driven by hydrogen uptake. So you can monitor over the period how the hydrogen is uptake is there. So certain stage it will be flattened. It indicates that your reaction is completed. Again, third way of monitoring is calorimetry measures. The thermodynamics hits in all the steps highly exothermic reaction. So you can monitor the reaction with the heat flow. Over the period that the heat flow will be stopped, that it indicates that your reaction is completed. So figure shows that clearly 3 methods are excellent agreement. So you can monitor the reaction not only with some TLC, you can monitor whatever that equipment you have, you can monitor, and inside the reactor, that is called RPKA. I will give one of the example specific case study also. This is one of the transaminase enzymatic reaction, which we are handling more. And I'm not, again, this is like a huge topic, how that mechanism, what is going on, the detailed mechanism I'm not going. I'm just an example, I'm giving that this reaction, if you see, it's a transaminase amine transferase, the byproduct is acetone. So if you want to, this reaction is equilibrium, if you want to driven the reaction in the forward direction, you have to remove the acetone from the reaction medium continuously. Otherwise the reaction will take place in reverse direction. So if you want to push the reaction in product direction, you have to remove continuously acetone. This is the challenge actually. So people can give the suggestion that vacuum or nitrogen sieves continuously you can apply, that it can evaporate, that acetone can remove from the reactor. But how in plant scale, in larger reactor, how we can monitor that acetone continuously removing? Because if some setup, any problem is there, again, this process will be not successful. So we need to some setup that monitor the acetone conversion in react IR. So it's like, again, olden days technology, like IR probe, you can insert to the reactor. By that way, you can monitor that acetone equivalence. So certain period, acetone equivalent is more. So when your acetone concentration is decreasing by using vacuum or nitrogen, then conversion is increasing. So your reaction is proceeding in the forward direction. So it indicates that clearly acetone conversion is, acetone is going away out from the reactor. So how we are monitoring, that is by inserting the react IR probe. It's like a IR probe. It's like one sensor. It's earlier days, if you see that one RB flask, one bead will be there, the reaction will be setting. But now you can see that this is a modern chemistry. You need a temperature sensor, probe, pH monitor, pH, what is the changes in pH? This is the pH probe. And again, vacuum applying. Again, this is the react IR, this is a probe. So continuously, you can monitor that acetone. Initially, acetone production is less because reaction is just starting. So over the period, acetone is increasing. So here, this is the equilibrium steady state. Again, if you remove the acetone by vacuum, conversion is increasing. So you can plot that acetone concentration versus conversion. So end of the reaction, acetone concentration is less than less than 0.2%. Conversion is 96%. So it is like a pictorial representation. It is giving that what is going on inside the reactor. So if you want to see that a classical way of mechanism, you have to study that what is the impact, what is the temperature, maybe where the color changes is, the product quality should be yellow, white and yellow color is coming. So maybe a lot of probability. So this is one example. If you want to insert like this react Raman is there, react UV, whatever probe, whatever sensor, maybe temperature, if you want to observe, put the temperature sensor and observe it. Maybe it's a whether endothermic reaction, exothermic reaction. What is the relationship between your reaction progress and your product conversion? You can measure. This is also one of the recent techniques. Again, coming to the last, the biocatalysis. This is my own research area. So here, why we are using biocatalysis? Everybody knows that these are biodegradable and operation buffer-based reaction. There will be no solvent requirement and very specific reaction, either chemoselective, regioselective, or stereoselective, and renewable sources. So because of that, all the it's naturally green sources. So one of the exactly all the 12 principles will fit into the biocatalysis. So again, classification of the 6 classes of enzyme, and out of all the 6 classes, mostly hydrolysis and oxidative. These are the 2 important classes in industry. One of the case study, again, it's like it's a very interesting example. Most of the places I used to give this example. It's a high volume and low value product. So it's a pregabalin is the many people actually use it. It's a over counted. So medical stuff. Many people use actually this drug. This is a publication, academic publication, initially in the 1994 bioorganic medicinal chemistry letters. It's like a 10 steps, 33% overall yield. Cost was 6 times targeted process. This cost is around 4,000 per kg. Now that initially 1994, it's a 6 times more than that expected cost, and 10 steps you have to move. You have to go. So that chiral acetylcholine alkylation based Evans chemistry, that is the major chemistry involved in that. If you want to go for that, again, that Pfizer actually they developed some industrial process initially based on that chemical resolution, mandelic acid. So it is amino acid, beta amino acid, and mandelic acid resolution. Overall yield is 25.29% overall yield, 99.5 E. E factor is 86. So if you calculate the E factor, 1 kg of pregabalin, they have to generate 86 kg of waste. So again, waste generation is the biggest problem here. Though they are getting the enantiomeric excess better, yield is okay reasonably, steps also reduced, but the problem is waste treatment. Again, coming to the enzymatic steps, this is a cyanodiester. One isomer is selectively hydrolyzing. One isomer is unreacted diester. So here in that way, they can get that this E is different. This is enantiomer selectivity. So how far the selectivity of the enzyme. So reaction is entirely forwarded. They optimize it in water, enzymatic resolution in water. Again, next is a branded nickel reduction, cyano to amine also in water. So in that way, all the reactions are they optimized in water. Overall yield is 90 to 95%, 99% purity and 99.7% E. So theoretically 40 to 45% yield, because in resolution always 50-50 only. So 50% again unreacted isomer, they have to recycle by racemization, chemical racemization. So in that way, the E factor improved 86 to 17. In the enzymatic way, it is a 17 kg of waste actually. Again, that is end of the day, that waste is enzyme plus water. It will go to biotreatment plant, and the product will be coming out actually. So there will be no hazardous reagents and all the operational safety. Nothing is there. Again, the story actually not end, because again the problem, if you see that they got award and it is industrialized, commercialized, but still the problem is 50% of the isomer, other isomer they have to recycle. Again, number of steps is slightly more. So here in that case, 1 ton pregabalin, if they want to make the first generation route, mandelic acid salt resolution, they need 57,000 kg of starting material. Here 11,000 kg of starting material. It's like a 5 times less input. Because of that improved yield and purification, they need 5 times less input. And particularly if you see that mandelic acid, here you need stoichiometric amount. Here there is a catalytic amount of enzyme only. There is no need of any stoichiometric amount. This is a major contribution for that waste generation in chemical route. This is again the solvent, all the reduction. So what we are doing further? So here you can see that 50% again they are going to as a racemization. So can we modify the scheme instead of getting the single isomer, or maybe in situ DKR, dynamic kinetic resolution, without isolating separately, and in situ can we able to do that kind of research in our lab? What we are doing. This is first generation route, mandelic acid resolution. Again, if you see that enzymatic resolution, similar, that same chemistry replicated in similar way. This is one of the industrial process, diacid desymmetrization, anhydride, again ammonia ring opening, again Hauptmann degradation, pregabalin. So this chemistry now most of the industry people are following. It's a similar way can we do with enzymatically. So here if you see the diester to diacid to diester, if you see the comparison with this molecule and this molecule, this is kinetic resolution, this is called desymmetrization. It's a symmetry molecule. After reacting with the enzyme, it will give either wanted isomer or unwanted isomer, but it explosively single isomer will be there. There will be no other isomer. So again, the same chemistry. Again, ammonia, amidation, again Hauptmann degradation, that pregabalin will be there. So it's a choice is different. Depends that what the industry they have the capability, what type of expertise they have. Depends upon the expertise and whatever the facility they are choosing any one of the method. But if we see that cost efficient wise, obviously the first one is no, because of that E factor 86, because now that they need to close the industry, that they are generating more waste. So obviously second route, third route, fourth route, any one of the route they can generate from that optimize, they can adopt the route. And what we have IACT capabilities, high throughput screening facility, we have enzymatic process development, we have scale up studies and scale up for plant scale production. For example, this also we scaled up in 200 kg scale. And enzyme immobilization for continuous recyclability and continuous flow biocatalysis also we have the facility to increase the productivity. Again, particularly for enzymatic case, if you add some mechanical stirrer or bead, will rupture will be there, protein rupturing will be there. To avoid the continuous flow chemistry also we are using some of the cases. And ongoing research, screening and characterization of novel microbes for biotransformation, fermentation based small molecules, and advanced science studies on enzyme transmissivity. Actually, other than known application, we are also studying. And one part reactions, process development and intensification using emerging techniques, and the estimation of protein contamination. So in that way, normally if you see the regulatory aspect, what all the contamination, what all the impurities are available, you have to give the data. When we are using biocatalysis as the enzyme as a catalyst, we are also able to give that what is the protein contamination in your final API. That is also important aspect. So these are some of the case studies what we are doing. As I mentioned that flow biocatalysis here, you can see that small amount of substrate meeting the large amount of catalyst, so that the inhibition is, this is the product inhibition zone. So your conversion will be 100%. You will get the end of the reactor, you will get the 100% conversion. We applied recently, we published some OPID paper by one of the airplane. This is an anti-cancer drug for the airplane kinetic resolution. We used this chemistry, and one of the saxagliptin amidation also we used this chemistry. Presently, we are doing some microbial hydroxylation, cytochrome P450, and steroidal transformation also we are working on that our area. And we have also 7 liter capacity fermenter we have in for bench scale optimization, and the spinning basket reactor and multi-mode high throughput screening facility also we have. And more than important that it's like my end of the presentation, I want to say that all the modern technology, whatever facility, everything available also, what we need is again ethics and plagiarism is the more important crucial point. Normally we used to tell that do or something you can do and you can publish like that. It's not like that. Better not to do is better. If you are not confident about your data, if you are not confident about your results, better not to publish. That is important, because ethics is more important in the research. Recently, you can see that 127 papers retracted from India. It is not only from India. I just kept as a screenshot, particularly more on China. We can't believe any of the publication mostly. Another thing is not only from Nobel laureate also faced with this problem, data integration, image duplication, fabrication of the data. So many problems are going on again out of that research area. Now this is the biggest headache for everybody for ethics in research. Here you can see that the same red was living in almost the 10 years. They are using the same data for, you can see that maybe B that 3 and 4 are similar to 5 and 6. I think these 2 rat pictures are same, 2 different papers. So it is very surprising that how that rat is they are using for the similar data. These are some of the plagiarism kind of oriented things. Better we should avoid these things and all. If you want, you can read that ethics in plagiarism is a huge topic title. So we should follow in our research. That is what whatever we are doing. Maybe we can do some good science in the ethical way. That is a better idea. So take home message is before taking to the PhD and research problem, finalize the area of your interest, and don't bother about your facility, what is available in the institute. There is no facility available, not available. I just kept that as I'm right hand side some of the pictures. This is the DC motor, olden days, the tape recorder motor. My guide actually, he used to give, this is the like a overhead stirrer. If you see, this is the overhead stirrer. We don't have that kind of much facility in our student time. So he used to buy most of this tape recorder motor, and he used to assemble with some of the pipette, our pipette, and he used to make us a overhead stirrer. So in that way, we also use and we publish in many papers. So facility is not a limiting factor. We can assemble, we can create a portable model always based on our requirement. So important thing is your interest and your area of interest and your willingness of the work interest is important. So understand the fundamental issues and the country's requirement in that area and your surrounding neighboring area, and try to improve the existing process. Whatever they are doing, maybe the dye industry, road, whatever that people are doing, maybe classical process, try to change their process or they try to improve their process, how effectively they can improve the process, and become an entrepreneur after degree. No need to search for a job, for applying job and all. So we have that over the period 3-4 years, we should have like a technology and we should try to accommodate, and the ethics in plagiarism in scientific publishing, IP issues. So these are the take-home messages I want to give for particularly for youngsters, BSc and MSc students. And these are some list of interesting publications and some of the patents. I kept like a number of PhDs awarded 25 because I'm from the same lab and from Dr. Fadnavis. He is my guide. I'm the last student of my guide, and so over the till now that around 25 people graduated in that degree awarded in the area of biocatalysis. This is our laboratory fixtures. That our lab inaugurated by 1996, and these are some of the facility. So I am luxurious enough that I am fortunate enough that my guide time we don't have this kind of reactor. You can see that here one small scale 1 liter reactor. This is the, but I am now have the fund and I am able to establish some of the facility which we don't have in our student time. These are the UPLC and HPLC. This is the fermenter fixers, and this is the safe flask and temperature Zulabo, the high throughput screening facility. These are the facilities I have, and this is my laboratory fixers. And this is IACT recent pictures. During Independence Day, we clicked some of the pictures. This is our main building administration, and this is the main entrance in road view. And this is our discovery building where my laboratory is there, and we are sitting here. And this is some pictures of Hyderabad, and we have many tourist spots in Hyderabad, particularly so women college. Maybe I can tell that pearls and bangles and dress material available very cheaply in Hyderabad, and it's a land of biryani. It's famous in Hyderabad. And finally, I would like to acknowledge that our IACT director and the team OSVC, my guide Dr. N.W. Fadnavis, and my past company Dr. Reddy's Laboratory, and the organizing committee, Department of Chemistry, DKM College for Women, and all the organizing members, everybody. I would like to thanks for the wonderful opportunity to give the presentation, and thank you. Thank you, ma'am.
Thank you, sir. On behalf of Department of Chemistry, my sincere gratitude to Dr. T. Kumaraguru sir for his valuable presentation. Sir, you have effectively explained about fundamental issues in recent research. I hope your talk would lead a fruitful key for the upcoming researchers.
Any questions or anything is there also? Maybe you can ask or you can mail me also. I can answer it.
Yes, sir. Participants, kindly post your queries in chat box. If any queries is there, you can unmute and you can ask.
Yeah.
Sir, no more queries, sir.
Yeah, okay, madam. Thank you.
Thank you, sir. Next, I would like to invite Dr. T. Komati ma'am, Organizing Secretary and Assistant Professor of Chemistry, to deliver the vote of thanks.
Good afternoon, all. On behalf of the Department of Chemistry and my own behalf, I feel privileged to propose the vote of thanks. We know that gratitude is the best attitude. Gratitude creates the most wonderful feeling. It can resolve disputes, it can strengthen friendship, and it can make us better men and women. First of all, I would like to express my sincere gratitude to God for showering His blessings to this wonderful occasion. I would like to thank our special guest, Dr. T. Kumuraguru, scientist, Biocatalyst Lab, IICT Hyderabad, who, despite his busy schedule, has accepted our invitation to grace this occasion and delivered the talk on the topic recent trends and advances in organic chemistry. Sir, really your talk will be more helpful for us to implement a new research finding. Your lecture is much interesting and thought-provoking. I'm sure that all the participants have taken your suggestion. Thank you, sir. I express my sincere thanks to our President, Dr. T. Shivakumar, sir, our beloved Secretary, Dr. D. Maninathan, sir, and our respected Principal, Dr. P. N. Sudha, ma'am, for giving support in all our activities. I extend my sincere gratitude to our head of the department, Dr. M. Nagaratnam, ma'am, for helping us whenever and wherever there is a need. I wholeheartedly thank the organizing committee for the good initiative, fine efforts, involvement, and their willingness they have expressed to take on the completion of the task. I express my sincere thanks to our beloved students who are the pillars of our department, and I express my sincere thanks to all the staff members from our college and other colleges who have attended the program and make it successful. Once again, I thank you one and all. Thank you.
Feedback, please.
Thank you, ma'am. Participants kindly fill the feedback link which is posted in chat box.
Yeah, thank you, madam.
Thank you, sir.
So I can close it, right, madam? Or I think somebody raised the hand. Maybe some other people, maybe yeah, through somebody. Yeah, if you want, you can ask that question. Maybe somebody raised the hand, madam.